What's up, music nerds? This week, we're looking at Chapter 2 of Hermann Helmholtz on the sensations of tone. Now, if you haven't watched my video on Chapter 1 yet, definitely check that out. And the link to the web book that I'm reading from is in the description. The entire text of the book is there, as well as all the apps that I'm going to be showing you in today's video. So let's get going. Chapter 2, on the composition of vibrations. At the end of last chapter, we came upon the remarkable fact that the human ear is capable of separating the musical tone produced by a single musical instrument into a series of simple tones, namely the prime partial tone and the various upper partial tones, each of which produces its own separate sensation. We will first investigate the nature of the motion of the air when it is produced by several simultaneous musical tones, and how such a compound motion is distinguished from that due to a single musical tone. He describes this using the analogy of throwing stones into a body of water. When two stones are thrown at different points, each will produce a ring of waves, which will expand and eventually meet each other. If they meet where both waves peak, the peak will become higher. If they meet where both waves trough, the trough will become lower. And if they meet somewhere in between, it'll even out. The Animations for Physics and Astronomy project has a really good animation of this. The same thing is true in a room full of different sounds. When several sonorous bodies in a surrounding atmosphere simultaneously elicit different systems of waves of sound, the changes of density of the air and the displacements and velocities of the particles of the air within the passages of the ear are each equal to the algebraical sum of the corresponding changes of density, displacement, and velocities which each system of waves would have separately produced if it had acted independently. So in a sense, each system of waves coexists simultaneously in the air, and our ear is actually really good at distinguishing them. Now you might remember from last chapter that the pitch numbers of upper partial tones are multiples of the pitch number of the prime tone. So now he states that when all musical tones which are intermingled have pitch numbers which are all multiples of one and the same old number, then these musical tones, as far as pitch is concerned, may be regarded as upper partial tones. He shows this to us in figure 11. We have our prime tone here, and curve B here has a period of 2 times that. Now, if these waves were to be playing simultaneously, they would create this wave, wave C. And Helmholtz actually suggests that you take a piece of graph paper and plot this out by hand. Starting with 0, then B1 plus A1 is C1 here, and then A2 minus B2 is C2 here. And the dotted line is our initial A curve, just for comparison. So this curve, curve C, has the same period as curve A, so it would be the same pitch. Now what happens if they're not played exactly simultaneously? For instance, shifted curve B slightly to the right. Well, we'd end up with curve D, which is a different shape from curve C, but still has the same period. With this app, we can hear that changing the phase doesn't alter the pitch. In figure 12, he shows us wave B, which has 3 times the period of wave A, and their composite here, wave C, which has a slightly flatter top. If you shift wave B over, you end up with curve D here. Now, wave A and wave B are both single simple tones, the kind of wave you would get from a tuning fork, which, as we remember from chapter 1, is the only type of wave that does not produce upper partial tones. whereas curve C and curve D, these composite curves, are the kind of thing that you would hear from a musical instrument when you hear the primary tone as well as the upper partials. In fact, he says that those waves give nearly the same motion as a single closed organ pipe of the narrow kind. So there you go. At this point in the chapter, we get to Ohm's law. Every motion of the air, when corresponding to a composite mass of musical tones, is, according to Ohm's law, capable of being analyzed into a sum of simple pendular vibrations, and to each such single simple vibration corresponds a simple tone, sensible to the ear and having a pitch determined by the periodic time of the corresponding motion of the air. And this app is going to do exactly that for us. We're going to sketch whatever weird-looking function we want. And there we go. Here's a weird-looking function. We can hear it. And this app breaks it down into the sum of these simple pendular vibrations. Let's hear that. Can your ear hear the difference between one tone and multiple? Maybe we gotta stick our earphones in for this. Let's try a different curve. Now this brings us a little bit closer to understanding the mysteries of quality of tone, because when we hear a smoother curve, we're going to hear more of the deeper partial tones, the ones closest to the prime tone. And when we see a curve with angles or sudden changes of curvature, we're going to hear more of the upper partial tones. Let's try and hear this in the app. Definitely put on your headphones. First, let's sketch a nice smooth function. And here, the harmonics. I definitely mostly hear that prime tone. Now let's sketch a more angular function. Yeah, I do hear more of the upper partials. Or maybe it's confirmation bias. Let me know what you think in the comments. He ends the chapter by saying that just because we can analyze any sound as a sum of simple pendular vibrations doesn't necessarily mean we should if we're trying to understand sound in nature and not sound mathematically. We shall inquire whether the analysis of compound into simple vibrations has any actual sensible meaning in the external world, independently of the action of the ear, and we shall really be in a condition to show that certain mathematical effects depend upon whether a certain partial tone is or is not contained in a composite mass of musical tones. And that's the end of chapter 2. If there's anything that you want to read in more detail, or if you want to try out those apps for yourself, go to sensationsoftone.com. And I will see you here on YouTube next week with chapter 3. I'll see you then. Bye!